So, good afternoon, good evening. I am sorry that we are taking a little bit of your evening on a Sunday to do this, but yeah, we had to make the schedules work a little bit. So we're going to be going over a little bit of PCB design basics. So touching a little bit on process, but I know that y'all have designed boards, so y'all know a little bit of the process. So we're not going to dive too much into that, but we're going to look at some tips, tricks, not KiCad tricks, but general design guidance and some best practices on some things, so that as we make new designs going forward, we know what to look for. You know, some things are a little less obvious than others. So let's just go right into it. A little bit about me. I graduated as an ECE from this past May 2025. When I was around, a few of you might have seen me around always in the pool room, and that was kind of the legacy that I had as a pool player. I was part of Formula, but for spring of 2022, so not too big of a legacy, but I was part of the Mark V effort, and so I designed the sensing controller board. I'm not sure if it actually got on the car or not, but it should be somewhere in the GitHub. And so my experience in this, I've worked a year on and off, pseudo internship at a CCA assembly house. So that's where I got a lot of my experience in building the circuit card assemblies. So CCAs are circuit card assemblies. And now I have about a year experience in actual printed circuit board design, working at RTX here in Tewksbury, where I've been primarily focusing on radio frequency design, mixed digital and analog design. Not too much in power, not too much in HDI or memory, but a lot of these things can apply. And so getting started with some pre-layout, we have a few assumptions. As with any good engineer, we have to make some assumptions. I'm assuming that y'all are using KiCad 9, or at least the images and everything, all of the capture that I've done on this slideshow is using KiCad 9. I expect that, I think KiCad 10 just came out. I don't know if y'all are rolling in right into it, but it should be very similar still. But everything here is in KiCad 9. But one of the most important things before we even get to layout is I'm assuming that you've gone through extensive review of your schematics, or at the very least that y'all are confident and sure in your schematics, because having a good schematic really does go a long way. It helps you really be able to identify the requirements of the design. So if we're talking high power, differential pairs, etc., all that good stuff. If you have the backbones of the schematic, that's going to make the layout quite a lot simpler and easier to follow, especially if you're receiving the layout, receiving the schematic that you did not work on. It's easy for you to work on your own schematic, but if you receive a schematic and then you have to design off of that, we're assuming that that schematic has been reviewed. We're also not going to be talking anything about component selection. We're hoping that already happened at the schematic level. So we're not going to talk about that. But generally speaking, avoid parts that are going obsolete, right? Because we want to be able to purchase the parts that we're designing for. And we're only going to be covering really topics on 2 to 4 layer boards. And I'm assuming that we use standard 62 mil or 1.6 millimeter boards, primarily 1 ounce boards. And we are using a 4-4 material, which is kind of like the golden child of all dielectric materials. I'm also assuming that we are working with through-hole designs, so we don't have any partial holes or half-drilled holes. I'm assuming that all of our holes are going from all the way through the board. I assumed PCB way, although I was just informed that I think we're using JLC PCB, but it should work either way. The requirements are very similar. And generally speaking, whenever we talk about PCB manufacturing capabilities, we always want to be way above that. Because whenever we're talking capabilities, that's like the bare minimum, like in an emergency. You know, like if we can't make a lot of room. Like if we have to route tightly, that's where you have to depend on the minimums. Otherwise, we want to use as much space as possible, want to have the greatest clearances that we can. So we're going to go a little bit into the manufacturing capabilities, but just double check with JLC PCB on what exactly those numbers are. And I'm also assuming that we're assembling these here, like we're not going to any assembly houses, so that we're placing either by hand or with a pick and place machine. Do we have a pick and place machine? Perfect. And I'm assuming that we're hand soldering all the through-hole connectors. Perfect. So we have to consider a few things before even placing any components on the PCB, right? We have to consider what do we need, both electrically and mechanically. So we start electrically, like what is our board doing? What is going on our board? Do we have communication protocols, right? Is it CAN? Is it SPI? Do we have both? Do we need differential pairs? Do we need to control our impedances, right? If we have controlled impedances, then we probably need to consider in our stack-up, we need a reference layer, a nice solid reference layer. So this is probably going to drive, do we need 2-layer board or do we need 4-layer board? Maybe, how can we place our components such that we can minimize via transitions? Because via transitions is just adding more length to that trace. So that's more length that the signal has to flow. Do we have any high power? How many powers do we have? Do we just have 12 volts, 3 volts, 3.3 volts, 5 volts, 7 volts? What are we talking about here? How many planes do we need? How much heat dissipation are we going to need? Are we going to have anything high frequency? I think the highest frequency that we have is 50 kilohertz, which is, in the grand scheme of things, not that fast. But we still want to pay close attention that we treat those like they're a baby, right? We want to put a lot of attention to that. And are we going to need shielding? Is this board going to be in a very noisy environment? Are there a lot of magnetics going on? How much shielding, how much do we have to protect our components?
So, could you give an example on what a noisy environment would look like?
Yeah, noisy environment. Primarily one where there's a lot of high frequency signals in particular. So if you have, I guess, high power inductors or a lot of switching going on. So a lot of MOSFETs going on, or if you have a crystal, even a high frequency crystal, those are going to produce a lot of noise. And they also have a lot of EMI radiation. And so you want to protect your boards from, I guess, it's not just EMI, but EMC, so electromagnetic compatibility between the boards. And so a lot of the time you have to have really solid grounds and really solid grounding in general, which is why we think about shielding. So shielding can come in two ways. We can either do it on board, or we could also do it off board. I don't think we do too many designs where you have to put any like EMI shields, like a physical block of aluminum, but that is a requirement sometimes in some boards. And so obviously you can't just put the components everywhere, because sometimes you're going to have a block of aluminum that is going on top of it if you have to shield it. But a noisy environment is usually one where you have a lot of electromagnetic noise going on. So magnetics, if you have a lot of transformers, inductors, switching MOSFETs, and crystals. Is that alrighty? And so those are some electric constraints. We also have, this is kind of a bit of a duh, but there are mechanical constraints as well, right? Because as PCB designers, we have to work very closely with the mechanical team. The mechanical team knows just how much space we have, knows where we can have tall components or where we need short components. And so ideally, you should always be receiving at the very least a DXF from mechanical telling you where to put connectors, because sometimes these connectors have to fit in a certain way. In this case, I think we have a lot of boards that are edge connecting. So the board itself is a connector, but sometimes you have other connectors. So work with mechanical on getting those exact locations. They should be able to provide a DXF that has the entire board outline. And so you import that into KiCad, and then that's your board outline. I think there's a layer called edge cuts that does that. And so, you know, work with mechanical. What shape do I have? Where are my mounting holes? Because obviously you can't connect parts where there are mounting holes. What is the orientation of all the connectors? Where's my pin 1 going, right? Because maybe I'm stacking on top of another connector. And if it's a stacking connector, you know, you want to make sure your pin 1 aligns with the other pin 1, right? You got to think about the entire system. And then mechanically, we also talk about surface finishes, which isn't so much reflected in the design, but definitely at the time of purchasing. I think we were talking about, we mainly go between Hassel and Enig, although I would also recommend considering a hard gold when we were talking edge connectors or anything that has to go through a lot of friction, a lot of connecting in and out. And we also have to consider our fine pitch parts. So I didn't see anything that was too fine pitch in the designs that I was sent, but we're talking about ball grid arrays or quad grid, land grid arrays. So anything where the pads are really close, right? And you have really tight spacing between leads, you can't just use any finish, right? Because sometimes you need the board to be very flat. And so HASL is not going to give you a very flat surface because it's just hot air solder level, right? You just put solder and just let the air kind of flatten it out. You don't have much control over that. Enig is immersion gold. You can get that very flat, right? So if you need a lot of really tight lead or tight packages, that's where you would have to work with whoever's going to actually make the purchase. Hey, you know, we need actually to order Enig instead of our hot air solder level. Because this is nice and cheap. This is your golden child for everything. It's the cheapest thing you're always going to have. This, since this has gold, it's going to drive up the cost, right? And so sometimes we do need that, right? And so let's not just always go for the cheapest option because it's cheap, right? So sometimes it's good to consider. So consider, do I have fine pitch parts? Maybe let's go for an Enig, something that's going to last longer and give us a nice controllable surface. And so those are some of the requirements, mechanically speaking. And so, as I mentioned, some of these things are actually going to drive our layer count, because if we have like sensitive signals that we need to control the impedance, and we have to have a lot of control over very specific and nitty-gritty details, then maybe we want to make sure we have a solid ground. And if it's a dense board, maybe we can't route everything on the surface layer. Sometimes we have to go into the second layer, right? But if that's going to make some cuts into our reference plane, then maybe we should consider moving from a 2-layer board down to up to a 4-layer board, so that we can conserve a nice solid ground, have enough room for our power planes, and then if we need to cross over some more signals, that's what we would do it in the 4th layer, right? And so this is just kind of some pros and cons, just generally speaking. We're going to go a lot into the stack up because I feel this is one of the things that as a PCB designer, we really have to consider early on and tackle it early on. And it's not really something that is very taught or understood because it's very much a manufacturing thing. But if the fab house cannot fabricate the boards that we want, then it's not really a good design. So we have to consider very closely, are we good with just 2 layers or do we actually need the 4 layers? Right. And so these are just some considerations before we even get started on the layout, right? And so we're going to go into, at the very least, the setup. In my opinion, a good board setup early on is just going to carry the entire design, right? So before we even place any components, before we even start any routing, we want to make sure that we have all of our constraints nicely set, because we do not want to, as we're halfway through the design, realize, oh crap, I needed a certain spacing on my traces. And then all of a sudden you have like half of the board built and it's not going to autocorrect itself half of the time. Like you're going to have to manually readjust everything. And that's going to drive up a lot of time, right? And it's also going to be a little frustrating. So we want to make sure that we set it up from the very get-go. And so in case you haven't seen it, it's that button, the green one with a cog. That's where we do all of our setup. That's where we're going to find a lot of the things we're going to talk about, at least in this part. Although I guess any questions before I get into this part?
Should we be following on from KiCad?
Not necessarily. You can if you want. It's not a tutorial because I'm not going to go into any KiCad specific things. If you'd like, and if you have a design that you're working or wanting to start, you can, and I'd be happy to help you all through KiCad, but it's not a requirement. You don't need to follow along in KiCad. Hopefully, it'll be easy enough to find these. I'll give you all a copy of this presentation in case you'll need it as a reference. Y'all are more than welcome to have this. I'm not representing Raytheon, and there's nothing proprietary in this, so you do not have to worry about that. So this is very much, y'all can use it as a reference going forward. And I'll give that to Henry to give y'all. So first and foremost, kind of an obvious, the dumb thing, we got to get our board outline, so which is usually in our edge cuts layer. And so in case y'all haven't seen it, hopefully y'all have seen it, you have to import the DXF, which is under File, then you go Import, Graphics. And so you get your DXF, and normally you want to actually put it in edge cuts. You can put it in user's drawing if that DXF has too many things, right? For example, this one doesn't have much, but if the DXF had the actual place for the connectors and everything, you want to be able to have that separately and then be able to reference or I guess build your board on top of the DXF. That is something that you can always do. Industry standard, normally the DXF is in inches, so you want to make sure that you're importing inches, and hopefully it should be to scale, right? Work with mechanical, assuming they're going to give you a DXF if it's a board that needs it, right? So that's going to give you the outline and the place for the mounting holes. I think currently we're doing mounting holes, a mix of edge cuts. Sometimes, I'm not sure if there's a mounting hole part in your library. If not, that might be something to look into as well. This is like the rudimentary way of doing a board outline. In industry, I mean, I guess I'll give a few little tidbits and bits of industry. We have this thing called an EMN and EMP file, which is basically a smart DXF, kind of. And so that is something that you can get from Creo, which is like SolidWorks, and it communicates directly with your PCB design software. And so in industry, it's a lot simpler. This is kind of the old-fashioned way of doing things. But put the DXF in the user layer, and then you can create it from there. It's kind of a like rudimentary thing that obviously we're supposed to do, but it's good to keep it in mind how to do it. And now we're going to talk into the stack up. And I apologize if I go too much into the stack up, but I can't emphasize enough how important this is. And so you're going to find this under, if you're in the board setup menu, you go under board stack up and then physical stack up. This is where you're going to determine how many layers you're working with. So we're either working with 2 or 4. Hopefully we have already determined, you know what, we have a lot of critical signals that we have to take care of. Let's go to 4, right? Or maybe we don't need that much. This is just a simple pass-through board or very little circuitry. We're good with 2 layers. And so this is where you would set everything. And I can't emphasize enough just how important it is to have this as accurately as possible, because you can always come back and reference this, right? Hopefully you're also keeping notes and documenting this somewhere else. But if push comes to shove and you want to know what your design needs, you can always go back and find, you know, more or less the information. Most modern EDAs will have the thickness in ounces. That's how we order our boards, 1 ounce copper, 2 ounce copper. There's a conversion. You can always look it up, what is 1 ounce copper in thickness. Or sometimes you'll be able to have a stack up that gives you the exact thickness, like before plating and after plating. And so we want to design to that. And so this is KiCad specific, but if we were to put this in any other modern EDA, EDA would be your design software, electronic design software. Sometimes they have field solvers, and so you'll actually be able to get your impedance control calculations in the software. You don't have to go and find some other calculator and then compare with your manufacturer or whatnot. Sometimes it's built in. And so going forward, if you do get into board design later on in your career, try to have your stack up as accurately as possible from the get-go, because that's going to save you a lot of time in trying to find those impedance calculations going forward, right? And so let's really understand the stack up a little bit more, because right now I've given y'all 2-layer boards, 4-layer boards, I've thrown controlled impedance, but what the heck am I talking about here? So as I mentioned, copper weight, I'm assuming that we're mostly using 1 ounce copper. Sometimes we might want to consider going at a higher copper weight. For the most part, for most digital things, y'all are just good with your 1 ounce. So you can always reference this table if you need it. All of the measurements that I'll be giving, or for the most part in this presentation, are all in mils. So thousandths of an inch. That's just more or less how we do things. Some manufacturers are going to have things in millimeters. So always be careful to make the conversions from millimeters to mils whenever you do any of these calculations. But copper weight is a design thing that we can choose. For the most part, we're assuming 1 ounce all the way through. So let's look at a 2-layer stack up. This is your bare bone easiest design that you're ever going to encounter. And so since we're primarily working with 62 mil or 1.6 millimeter boards, mostly all of the time, I want to say 99% of the time, this is going to be how it's built. So you have a core material that is roughly 59 mils of material. This is all glass fiber epoxy, right? It's woven glass fibers in an epoxy resin. And so you can have it in 2 types. You can have core material, which is nice and firm, or you can also have what we call pre-preg, which is like a sort of a glue. It's not exactly like a fully cured resin. In this case, for a 2-layer stack up, we're always going to have a core material with the plated layers on the edges. And when I say plated layers, I have to clarify that, at least in the PCB manufacturing process, I'm not going to dive too much into this. You always design, or when you're designing something, you're designing to a finished thickness. But when we're talking edge layers, since we have copper pads that we want a certain adhesion to, what the manufacturers do is they actually do about half of the thickness, give or take, and so they engrave, or I guess the term is etch the copper in this case, 1/2 ounce, and then they plate over so that your final thickness is 1 ounce. And so I mentioned this because when we're talking signal integrity and making sure that we are controlling our impedances, that assumes we have a very controlled and set thickness to the copper. However, generally, and this is just best practice in industry, doesn't affect us too much, you want to make sure that your controlled impedances are 100% solid. They're never going to be thicker or less thick. But since we're plating over, so we're adding or depositing extra material to try to match that, that can be plus or minus some sort of tolerance, right? So they're going to try to be as close as possible always, but it's always a risk. And so ideally, in this case, for a nice solid 2-layer stack up, we're going to have all of our signals on 1 layer. All of our components are going to be on 1 layer. And then on this layer, we're going to have a solid ground. Why do I need a solid ground? That is because when we're looking, and I didn't write this down on the slideshow, but whenever we draw any circuit, and hopefully y'all can see this, I know it's not going to show up in the camera, but whenever we have any sort of circuit, it's always a closed loop, right? The current must always return. We always have a return current to our reference, which is usually our ground, right? And so this is in an ideal circuit, right? Where traces do not have any resistance, inductance, or anything. However, since we have a board, and let's say we route everything on one layer, fine, the current flows nicely on this layer, but then we have to go back down. And so since electrons will always find the path of least resistance, right? This is just kind of rule of thumb. It's always going to try to go underneath the trace, right? So if we route everything on, let's say where this line is on the top layer, we're going to want to come back down immediately below it to make that loop as short as possible. And so you always want to be able to have solid copper underneath. Now, the problem with this two-layer stack up is we have 60 mils of a difference. So now you have a return current or a return loop that is really tall. And so if we're working in fields, we have a large field going around the entire board, right? So you can think of our electromagnetic field going across all 62 mils. And that's generally not great. But for a two-layer stack up, this is the best that we can do. Because if we have like a blocky or not a solid plane, then that field is going to go even further out because it's going to try to find a path if we don't give it a path, right? So this is a limitation of the two-layer stack up, and that's what I mean with the cons. Because you have such large dissipation, electromagnetic dissipation, it's a lot harder to really control your signal integrity. You can get pretty good, but we can do a little bit better. And that's where we have a four-layer stack up. And so originally, I remember when I was first designing my first board, it was a four-layer stack up. I imagined all four layers to be equidistant. But that is not the case. When we're manufacturing a four-layer stack up, we actually have to still have this core material. And the core material is always going to be as large as it can be because it needs to be sturdy. And so what we have for a typical four-layer stack up is we have roughly about 40 mils of this core material. Then we have this 1 ounce layer. And then we have the prepreg, which is a sort of a glue, right? This is not as solid and as tough as the core, but it's good enough that we can get some good adhesion of this layer onto the whole board. And so this is how a four-layer stack up actually looks like if you were to just chop a board in, I guess, in half, right? Obviously not to scale. But so what you may have noticed is we can choose this layer to be our reference, and all of a sudden, instead of having to go all the way up, right, to 62 mils, we can get a nice closer loop where this is only really about 7 mils. And so I note a little bit of an ideal use case, or one of the many ways to use it, is to have all of your components on the top layer. That's where all of your critical routing is going to be. And ideally, there should be a copper port, and I'm going to go into that soon. So top layer. And then what I want to see is a nice solid ground so that we have nice short return loops, right? So that we reduce the electromagnetic radiation and inductance. Because also when you increase the loop, you add inductance into the system. So by making this loop bigger, or if we keep a big loop, we add a lot of inductance. And so by shortening this loop, we reduce the inductance, we reduce potential ringing and signal degradation, right? And so that would be a good use case of getting a nice reference plane, nice and close. Then if you have a bunch of power, so say a lot of components that take 5 volts, but a lot of components that take 3.3 volts, you can make the planes down here, right? You have all your copper planes nice and far away from your delicate signals. And then down here, what you can do is just balance it out with copper. Or if you do need to cross over a bunch of some signals that you couldn't get on the top layer, and if they're not too important, you can just chuck them in there. Simple, slow digital signals do not suffer too much from having to travel that distance, right? So that's what a 4-layer stack up looks like. And so I kind of went over the pros and cons. And this is essentially what you would see of your manufacturer's capabilities for a 4-layer stack up. This is a 4-layer stack up from PCB Way, where it's using 1 ounce copper. And so I used those exact measurements to make the the graphic before. And so it's not as clear when you're just looking at numbers, but you know, it's a pretty big difference, right? From an equidistant stack up to this. And so the con, of course, is you add more copper, more layers, more processing, drives a higher cost, right? So if they weren't, you know, depending on your budget, there may be a reason to keep things as a 2-layer board. But generally speaking, if our concern is signal integrity and keeping nice, clean designs, I would always recommend a 4-layer board. But if cost is an issue, then there are ways to also design a 2-layered board so that you can reduce some of these parasitics. So this is just a side-by-side, so we can look at, you know, there's a pretty big difference whenever we have to cross from top layer to bottom layer, or if we have shorter, a shorter loop, right? Any questions on the stack ups?
Is the signal traveling through or like between the pads by via?
So we're going to talk about vias in a bit. So obviously when you have a via, so if we have a via at the very top trying to get to the bottom, obviously the signal has to cross through. And so if you're going from there to there, your signal is traveling 62 mils down the via. And there's no guarantee that that via is shielded because it's just going across a bunch of FR4 material that can also have signals around it. So you generally want to avoid via transitions as much as possible. That's a nice golden rule. And so, you know, if we had more layers even, so if we had a 6-layer stack up, right? And if we had our signals, give or take here or here, going from 1 to 3 is a nice short loop, right? You know, your signal doesn't have to travel as much, but there's a caveat. And that caveat is you still have a plated hole that goes all the way down the board. And that can be a problem because now you've created an antenna, right? And so there's pros and cons. Sometimes if everything is going to be via connections, yeah, this is going to reduce that because you're always going to have copper on both sides. Whereas if you have a higher layer board and you're only going from 1 to 3, all of a sudden your 4 to 6 is an antenna. And there are different ways of getting different via stack-ups. We're mostly going to focus on through-hole vias because they're easier to manufacture. Basically, all you do with a via, we're going to talk about them in a bit, but basically it's just a drill that you plate with copper. And so the easiest manufacturing thing is always going to be a through-hole via. There are other types of vias called blind vias and micro vias. I can talk about them later, but I guess short answer, yes, if you have a via connecting 2 layers, your signal can connect from layer top to layer bottom through a via.
Okay, yeah. I guess I was just like looking at this visual, like wondering how the signal like traveled between.
Yeah, it would be through a via going straight top to down. Sorry, I didn't understand that from the get-go. But yeah, so you would connect from one layer to another using vias. But when I was talking about the return current, I was assuming that we trace everything over here. But you know, there's always a positive and negative side to any component. And so ideally you would have a ground via that goes in, that taps into your ground. And so your ground reference would connect through a via. So any connection is done through a via or any through hole, right? Because you can have a connector. I guess I didn't talk about this, but you can have a connector that is through hole, but you do not have to go in from the very top. And this is kind of something that I go into one of the pitfalls, because I noticed that everyone, or a lot of the designs that I looked at, they were starting in the top layer and then VAing into an internal layer, but you could have just started from the internal layer, because your through hole is like a massive via, right? So you can always, if you have a bunch of through hole connectors, utilize the fact that they're through hole, you know? So we can go into that when we get to the vias. And often when you get a stack up from a manufacturer, it's gonna have like your through holes, because you can manufacture different types of holes. But yeah, so vias are the ways that you connect different layers. So controlled impedance. I've tossed this term a lot, and I apologize, but it is something that we see a lot, especially with bigger boards. Why do we care about controlled impedance? It's normally we have in anything, and this is particularly true with radio frequency design, but this is general of most communication protocols. You have a source and a source impedance. So your source is going to have some sort of impedance. This is especially true when you're connecting two boards. And then you're also going to have a trace. In this case, it's a coax cable, but you know, a PCB trace long enough is going to act like a coax, or like a transmission line. And then you have your load impedance. You normally want to make sure that your load impedance and your source impedance and load impedance are the same, so that it's like swimming, so that you don't want to have a reaction like swimming through water and then swimming into honey, right? You're going to feel resistance. And that's not good, because that's going to do some reflections with your electrical signals. And so you want these two to be the same, source and load, but then you also want your channel to be that same impedance, right? Because otherwise we're going from water to honey to water. And that's going to cause a lot of reflections. And so we care about particularly higher speed signals to be able to control our impedances of the trace that we are putting on the PC board to be the same as our source and our load, right? And so how do we control the impedance of a trace? Well, there are a few things that affect our impedances. And there are a bunch of complicated formulas that thankfully there are calculators for, that we don't have to do by hand. So these are just some of the different configurations for traces. But for the most part, we're looking at single-ended traces that for the most part we're going to be designing microstrip. So microstrip is when you have your reference layer and then just copper on the very top or bottom, or there's strip line, which is basically a trace inside of the board. You have copper above and below. That's the difference. If you only have copper on one side, microstrip. If you have copper on both sides, strip line. For the most part, I think we're going to be focusing with microstrip for the most part. And so the things that we care about is what is our distance from our trace to our reference plane or to our ground. What is the dielectric constant or the permeability, the electromagnetic permeability of our material? So that core material, that FR4, is it, you know, like, is it a very compact filter per se, electromagnetic filter, or is it good against shielding electromagnetic radiation? Like, how easily does electromagnetic radiation flow through this material? Air also has a dielectric constant. So technically, we've already solved for that in the microstrip. When we don't have the reference layer on the very top, we just assume it to be air, which has a dielectric constant of 1. So that affects it, and how far, right? Because it doesn't, you know, or, yeah. So how far you are from the from your reference layer, and then also the thickness of the trace, like how thick is your copper. Those are primarily the things you're worried about when calculating the impedance. And then there's also coplanar spacing. So this is where you're controlling your impedance using a really thick ground plane, guiding it on the very top layer. We don't really do that much. That's more of an RF thing. I show it because it exists. And in fact, we want to usually design against it. We do not want to have coplanar waves if we're not designing for it, right? So dielectric material, trace thickness, trace width, height to reference, and coplanar spacing. So there are a few things that we can control here, right? We can't control the dielectric material. That's kind of predetermined for us. That's FR4. It has a specific dielectric constant. We can control the trace thickness, or that's 1 ounce, 2 ounce, 3 ounce, etc. For the moment, let's say we can't control that. All of the boards, the only copper in the world that we can get is 1 ounce. So let's not design for it. Our trace width, that is something that we can define. That's just how thick is your track, right? That we can design for. And then the height to reference. Depending on what you have chosen is your way of controlling it, right? The height to difference is how we discussed in our stack up. Are we gonna have to travel 62 mils to reach our reference? Or maybe can we save ourselves a little bit and with a 4-layer stack up, we only have 7 mils, right? So we can control that with the stack up, but you know, work to see if that's something that you can afford. I don't think it's an issue, but sometimes also time in manufacturing is going to be an issue. But point is here, we can design for the track width. And so this is why it's important that we are confident in our stack up from the very beginning, because now that we have all of the information from our stack up, now we need to find how big to make our traces. Because, you know, when I'm making a connection from point A to point B, you know, we want to make sure we've designed for the connection and not just an arbitrary, 10 mils looks good enough, right? Or maybe 8 mils is good enough, right? We want to make sure that we can back up what we're designing. Generally speaking, this is generally speaking, we want to design for 50 ohm impedance. Most everything, especially in RF, is sized and has an impedance of 50 ohms. And so if we return to our characteristic impedance image, if this is 50 ohm and this is 50 ohm, then our trace should also be 50 ohm, right? Naturally. So when we are talking single-ended, we have these two models. For the most part, since most of what we're doing is only 4 layers, rarely are you going to have a strip line. So let's focus on microstrip. Generally speaking, we get a nice rule of thumb. The larger the spacing, the wider our trace has to be to match 50 ohms. And basically what that means is the thinner the trace, the higher the impedance. You want to lower the impedance, right? You want to make it as easy as possible for the electrons to flow nicely. And so when you have a larger distance, you need to go, your traces also need to grow. And so also, just the general rule of thumb for all traces and all connections, to avoid coplanar effects, you want to make sure you have at least 2 to 3 times the clearance from trace to plane. And I'm going to talk about that a little bit more, because so far most of the designs do not have copper or have very little copper and planes. But I'm going to recommend shortly that we want to keep a nice balance of the copper all throughout the entire board. And I'll go into that a little bit. And so this is something else that you can set up. And you primarily set this up in the zone manager, is how far of a void you can have from the trace until you reach your plane, your ground plane. Because if it's too close, that's also going to affect your impedance, because then it's going to act like a coplanar waveguide, which we're not designing for. So we don't want that. And I'm going to show that in a bit. And so that's single-ended. And so I kind of did the calculations here, right? basically telling us on this one, the 2-layer board, the one that had a 62 mil, or was, technically it was a 59 mil gap between your top layer and your reference layer. In order to meet a 50 ohm target impedance, you need your track to be 105 mils wide. That is huge. That is 1/10 of an inch, right? And so that's pretty much unfeasible. We can't do that. And so that's why we'll always say again and again, you want your traces to be as short as possible, because we don't want this transmission line effect, right? Or we want to be in this high impedance as little as possible. That's with a 2-layer board. With a 4-layer board, it's a little easier. Since we have our reference so close, we only need about 11 mils of a trace to be at a 50 ohm impedance. And so the trace widths, or how thick the trace is not arbitrary, because how thick we make it is going to decide or how much impedance that line is going to have, which is going to be, how sharp or how harsh is that transition from honey to water, water to honey, or water to honey, honey, or honey to water, right? And so generally speaking, if we need controlled impedances on our board, almost always go for a 4-layer board, even if you don't have that many signals, because that's always going to give you the highest signal integrity, if possible, right? Because you won't need to design so big, and your impedance loops are always going to be shorter, right? And the same thing goes for differential pairs, right? In this case, we also have an extra factor, which is how far apart these edge-coupled connections are. Those are my rules of thumb. The closer the trace spacing reduces the impedance, but also, as we saw before, wider traces reduce the impedance, right? Because generally, we're going to start with pretty high impedance, and we're designing to try to reduce the impedance to be as close to 100 ohms differential impedance. And so it's the same thing as before, where, in order to, I think this is on the 2-layer board, it's a little better, only 36 mils for traces, but those are still massive. 36 mils, when you consider the boards that you're routing, that's a lot of space. That's a lot of copper, and they have to be spaced at 8 mils apart for that 100 ohm differential. But again, 4-layer board, we can get away with 6.5 mil traces with 5 mil spacing. So you're able to run more of those. You're able to run more signals around it, and still reach the same 100 ohms. This is particularly important for your CAN bus. I'm not sure if CAN bus is 100 ohms or 120 ohms. It's around that ballpark. You can look at the spec sheet or at the spec itself. But regardless, you're always going to be trying to hit that. You want to be as close to that as possible, especially since that is your highest speed or your highest frequency signal, right? So with differential pairs especially, try to hit this. And then with the single-ended, I forgot to mention, this is where your SPI lives. Whenever you have a SPI signal, think 50 ohm single-ended, right? Anything communication protocol, you want to make sure you're either 50 ohm single-ended or 100 or 120 ohm differential, always. And so best practices, ideally, you don't want them on external layers because, as I mentioned before, it could be slightly more, slightly less because of the process of etching. But in this case, close enough is good enough, I would say, as long as we're not like wildly off, right? There's still some process tolerancing. But we do not want them to be crossing over split planes. And so what I mean with split planes, and I'll talk about that later, but I'll marinate the idea with y'all, is if you have a solid ground, then you always have that nice straight return loop. But if you have a break, like let's say we have a power plane or something, then all of a sudden that return current has to go up and around to close the loop, right? And so that again adds parasitics into the signal. When in this case we're specifically designing them to have the least amount of parasitics, right? So best practice: do not cross over a split plane, and then also avoid the via transitions, because that's also adding more length and reducing that shielding that you have. But if you do have to do a via transition on a differential pair, shield it with some ground vias around it, so that all of a sudden you have ground also going into the board, which is pretty neat. But best practice, get it from your manufacturer, or you can also use a calculator. I used the PCB weight calculator for the images you saw. DigiKey also has a pretty good calculator. Little side note, technically, these calculators assume that you have no solder mask over the traces. Technically, the solder mask has a slightly different dielectric constant than air. For the most part, since we're not super high frequency, 50 kilohertz is not that bad, I would say this is good enough, at least compared to what we were running before, where we were just choosing arbitrary traces. Now we have a very close 50 ohm trace or very close 100 ohm trace. Good to know, that technically it's not always going to be exact, but this is definitely good enough and a lot better than if you didn't have any impedance control. And so this is where we get into the vias. So as I mentioned, we have through-hole vias, which is what we're going to have on our design. Then there's also buried vias and blind vias. I mentioned them because they exist. And you will find this when you have a really, really high density of signals where putting a via all of a sudden cuts off your routing for a bunch of other signals. Because obviously it's a hole. So that hole is somewhere where you can't route a signal, right? And you also need clearance around the hole. And so vias, when there's a lot of signals, can be a challenge. I was just working on a 20-layer board with a high density of signals where they only wanted through-hole vias, and that was a pain. So that's what buried and blind vias are for, is they allowed you to punch into the PCB only a certain depth, and then you can route on top or below or wherever you want. For the most part, we're just dealing with through-hole vias. These are good to know. I don't think you'll ever get into micro vias because those are more expensive. They add cost in processing, because basically you have to build it by layers, drill a layer, and then paste that drilled layer. So instead of having their sandwich and drilling into the sandwich, it's like drilling into the bread, the cheese, then the other bread, and then stacking them and hoping that they're aligned, right? So it's more expensive and not really needed for these use cases, but they exist. But what can we control about vias? Vias are actually the first fail point in most PCB designs, because they are quite literally a hole going into the board. A hole into anything reduces the reliability. It's easier to crush this. For example, if you have your chassis ground vias around a chassis hole, your screw is going to crush them, because that is weaker. You don't have a lot of material in there. So we're removing material. But also with vias is, since they make the electrical connection, these holes have to be plated, right, internally, so that, electrons can flow through the via. And so plating is done using chemical deposition, right? You immerse the PC board into and electrically deposit or etch and plate this copper, right? And so if your straw is too narrow, it's hard to get that liquid through. And obviously our solvent or solution has a certain viscosity. And so if we're dealing with too thin of a hole for a thick board, you're not going to get good plating. And then all of a sudden that electrical connection is no good. Because if you have a break here, then your via, you might have a hole, but you don't have a complete connection. You might have an open circuit here because your via was too small. And we don't want that, right? We want a nice solid connection. And so that's where we get aspect ratio. So aspect ratio is basically the ratio between the board thickness and the hole diameter, right? And so generally speaking, we want we want a lower ratio, because basically we want to say we have a bigger hole relative to the board thickness. Because if we shrink this down, our solution cannot go through. If we make this bigger, now our solution can go through, right? And so generally we want to stay between 6:1 and 8:1. And so what does this mean? For a 62 mil board, which is what we're running with the whole time, to get a 6:1, you need a 10 mil via. 60 to 10, 6:1, right? So for a 62 mil board, ideally for reliability, you want to be using 10 mil vias. And then on the other end, if you want to go with your smallest via, that would be your 8 mil via, which is your 8:1. So when we're, at least for the boards that we're designing, which are 62 mils, our vias should be between 8 mils and 10 mils. The smaller the drill, the more expensive the board. So I would recommend staying on the higher end of your aspect ratio. So a 10 mil via would be great. Now the highest that you can go, because you also can't make them too big, because then you have too much plating solution, is I think 5:1. So I think with a 62 mil board, you can, at the very limits of manufacturing, go up to a 12 mil via. But I would stick with 10. And you want to reduce the amount of different drills, because that also adds not just cost, but like processing time, because then you have to switch out the different drills. So, it's good to consider this as a design constraint, but it's kind of clear cut. Let's stick to 10 mil vias. And so the other thing with via design is the annular ring. So the annular ring is just how big that ring is. So if we assume that this is our via hole, not to scale, we need to have some amount of ring around the via, right? Because we need to make the connection, right? This plated hole needs to connect to copper, right? I don't know if that makes sense, right? So we need to actually make that connection. And, since manufacturing, it's not always going to be perfect. We try to get the nicest tolerance that we can, but you need to account for, at least with vias, this hole could be slightly to the left, could be slightly to the right, it could be slightly offset. And so if your annular ring is too small, then your hole might be too far off. You're not going to get a good connection or otherwise. And so in this case, PCBWay gives us the minimum annular ring that they can do. So you should design for bigger annular ring. But basically it is 6 mil annular ring. You don't want to go too big either, because bigger annular ring means less space to route, because this takes space on the board, right? So you have to find a good sweet medium. 6 to 7 mil is a good annular ring size, I would suggest. And so if we look at this as a 10 mil diameter hole with a 22 diameter pad, that gives us 6 mils of an annular ring, which is good. And so normally these should be defined already. I think you can define it in the board setup. You get trace widths, your vias, and then differential pairs. And so then there's this other thing called via and pad. Via and pad is going to be the most expensive via that you have, because in order for a via and pad, or VIPO, that stands for via and pad plated over or plugged over. And so basically, they're not going to do this automatically. You have to request this from the manufacturer. If you have a via and pad, you have to cap that and plug the hole so that solder doesn't go into the other side, or your solder doesn't flow through the hole, right? Because then that removes solder from the joint, and that's not good. And so you have to ask the manufacturer to plug the via, cap it, plate it over, and surface flat so that you don't have a bump or a divot, right? Because then your component is going to be shifted up or sideways. And this is especially bad if you have a lot of contacts on a part, right? So ideally, try to avoid it if you can. You can add them and request them, but do note that adds cost in processing. And then the other thing is tented vias. These are a little simpler because tented vias simply mean that the via has solder mask on top of it, so you can't actually access the via. So the thing about a via is if you don't tent it, and this is a choice that you can do in your board setup, right? Leaving your via exposed basically allows you to use this copper as like a test point. That's pretty nice, right? Because you can, ensure electrical connections and add some test points without adding them on the schematic. But then if you tent them, you can't access them. It's just, it's a choice. Often it's a matter of choice. The one time I would recommend tenting vias is if you have a lot of silkscreen, because solder mask basically covers exposed copper, right? If you have a solder mask clearance, then you have exposed copper. You cannot put silkscreen over exposed copper. And so if you have a lot of silkscreen, so like other designs and whatnot, and you have a lot of vias around, then your silkscreen is going to get all messed up. And so really the only real use that you would have in tented vias is if you have a lot of silkscreen. So like your reference designators or other designs like markings, because y'all track the revision of the board and all that, right? So if you have a bunch of exposed vias, then that's less places where you can put markings. Just a side note. Tented vias, good if you have a lot of silkscreen. But also, if you want to probe in and test the board, maybe don't tent the vias. And there's literally just a button that you can choose to tent the via, either in the top or in the bottom. It does solder mask almost automatically, so you don't have to worry too much. Oh, geez. The PCB capabilities. I took this from PCB Way. So if y'all do ever go back to PCB Way, y'all can reference this. Otherwise, y'all can go into JLC PCB and then go under Capabilities tab. And that's going to give you basically everything else that you need to configure your board setup. Ooh. Wait, did I read that right? All right. So layer, materials, dimensions. The ones that matter are your minimum trace width. So in here, we can go down to a 4 mil trace. I don't see why we would. Let's try to stay away from that unless it's absolutely necessary. So you can set your minimum to be 4 mil, but I would probably try to design for 10 mil upwards. Differential pairs, that's maybe where you can get to smaller traces, but try to be above 4 or 5 mils, because that's just simply what you can do. You can also choose your copper weights. And then this is where we get into like drills. So your smallest drill size is 0.1, well, it actually said 0.2, which is 8 mils. So you want all of your holes to be above 8 mils, 8 mils diameter. And then the annular ring, you also want to make sure you give it 6 mil annular ring or more, if possible. Miscellaneous, this is mostly set in most of the designs that Formula already has, but the character, width, height, half holes, which I think y'all do. I don't have a problem with these because I think y'all do this already. And then the surface finish, I've highlighted hassle lead-free because I assume we use lead-free solder. So a lot of cheap boards are going to be that, which is usually the gray or silver finish that you see on boards. Immersion gold is the ENIG, which is just that nice flatter gold finish. And then hard gold, this is what I'm talking about with the edge connectors, because you need a harder material if you're going to be slotting in or removing. There is a cost trade that you could do. If you're not, connecting them all that often, then maybe you don't need hard gold, because it is more expensive, right? Because it's more gold, more processing. So again, something that you can talk to amongst yourselves, since y'all are going to be the new leads, right? You can also talk with mechanical. How often are we going to be plugging these in and out? Do we need this? Is this in the budget? You can talk this to the project manager. And this is where you would set all of these clearances that we just talked about, right? This is a good frame of reference, I think, for references. You always want to have 25 mils copper to edge. That's to allow the routing bit when they're actually cutting out the PCB, like the major edge. That is always plus or minus a certain amount, like 10% or a certain amount of mils. So if you keep 25 mils from your copper edge to the board edge, that is good. And you can set that there, and it's going to take care of it automatically. We're not dealing with micro vias, so forget that. And then your silk screen, tuning, etc. And so you don't have to note this right now. I'll be sending this over. Oh man, I didn't realize how long this was. This is 85 slides, by the way. I think I think I can kind of breeze through these a little bit more. Mechanical driven placement. So now we're finally placing parts on the board. Of course, mounting holes, everything. And then, as I mentioned, hopefully you have a DXF that has all the rooms, that has basically where things need to go. If there are constraints, if there are no constraints, then we can move on to placing by schematic and looking at functional groups. I'm not going to dive too much, and this isn't like the perfect placement. All right, this is just a design I was able to find in the depths of my computer. But basically trying to highlight, you want to make sure, this is why it's important to have a good schematic, because a good schematic is going to tell you roughly where the components need to be relative to everything else. And so you can place by functional groups. In this case, you can break up the buck converter from 12 to 7 into the input side and output side, right? And so you can consider everything is in the input side, everything's in the output side. You can look at the LDO, which is placed nice and neat, or the other regulator, which is also placed out and about. And so this is mostly how you want to place everything, is using the schematic and defining your functional groups. The other important thing to consider in placement is your bypass capacitors. So in a schematic, I don't think this one's going to have many of those, but whenever you see VCC in your schematic, there should always be a 0.1 microfarad capacitor. And so you're going to want to use that capacitor to be as physically close to the pins, to the VCC pins, right? Because why do we get it so close? To reduce that inductance, right? The whole point of the bypass capacitor is to serve as a filter, because your plane or coming out of the via, it might bring a little bit of noise. If there's too much of a stub, then that's going to degrade the integrity of the power. And so you go through the bypass capacitor to actually then go into the pins. And so you want this to be as short as possible. You don't want to add back more inductance. And so when you're coming out of the plane, you want the VS to be as close as possible. Again, trying to close that or shorten that return loop so that you localize all the return loop there, so that when you go straight into the IC, it is as pure of the 3.3 volts as you can possibly have. And so if you have many capacitors, you want the smallest, which is usually the 0.1 microfarad capacitor, to be the closest to the pin. Then you can have all the other capacitors spread around. And you always want to do this with the schematic, because the capacitors and all the bypass capacitors are always going to have 3.3 and ground as their nets. And so if you just place everything that is 3.3 in ground, you're going to group all the bypass capacitors, but then how are you going to find the ICs that they belong to, right? And so you always want to make sure that you're paying close attention to the reference designator, because sometimes you're not going to always use a 0.1 microfarad. That's the standard, but sometimes a spec sheet might say, actually, we need 0.47 microfarads. So if you have a 0.47 microfarad bypass capacitor in a chip that requires a 0.1 microfarad, we got issues there. And so always place by the schematic, especially, and have a special attention to the bypass capacitors. And you also want to, I know we're technically in the placement phase, but you want to make sure you have enough room for those vias, right? Consider where the via is going to be going through and all that good stuff. Because otherwise you're going to run out of room, and then you're going to have not very good placement, and you're going to add back those inductances that you don't want to add back. And so also isolating noisy components as much as possible. So this is all switching, has a lot of switching. We have a crystal over there that is going to be susceptible to this noise. Here's the crystal. So we want this to be as far as we can from over there. And so that means grouping this away and having this in a separate ground plane that is connected only by a few traces. And so that's something to consider when you're placing by the schematic. Hopefully the schematic already tells you, or you're able to identify what has a lot of switching, what's going to introduce a lot of switching noises. So you can put that in one corner and then put all of your more sensitive components on another part of the board. And so when you're minimizing the rat's nest, always consider your most critical signals. So for example, your MOSI, or well, your SPI, your CAN buses, you want to make sure those are as close as possible, even within their functional groups. And you also want to make sure that your power is, you have your 5 volt circuitry on one side, you have your 3 volt on another side, so that your power planes are not crossing over each other or don't have to be weird and funky for no reason. You want it to be as clean as possible. So when we minimize the rat's nest, consider what is the most critical thing that needs to be the shortest, so our CAN bus, our SPI, and try to minimize that distance, even within functional groups. So some of the pitfalls is, oddly enough, placing components a little too close. Even though we have a pick and place, we still need to consider component heights, right? Especially for rework and solderability, or stencil, placing the stencil. If you're too close, then that makes it almost impossible to get a soldering iron in there, right? Or tweezers. So consider that sort of sizing. Typically, forgot to write it in there, but think about 20 mils pad to pad, usually enough for a tweezer to fit in there at the very least. And then placing components far enough away from taller components. So again, making sure that if you have a tall connector, that you don't have like a very tiny SMD or solder mount device right next to it, because then it's going to be almost impossible to get a soldering iron or even a probe in there. So trying to keep a little bit of distance, letting the components breathe a little bit. The only exception is the bypass capacitors though. So let's make sure the bypass capacitors are as close as possible. Always make sure you make room for routing. Consider how many signals are going through. Even though in placement we're not routing yet, we're just putting the components, you want to make sure you have an idea, where am I going to need the vias to be? Where am I going to need, how many traces are going to be going through here, right? And this is both in 2-layer boards and 4-layer boards. In 2-layer boards, this is even more important since all of your routing is on the top layer. 4-layer, you might have a little bit more concessions. But so consider your routing as you're placing. And then termination resistors should always be as close as possible to their load. So it doesn't make any sense to put this far away, since the whole point of this is basically impedance matching again, right? So for a CAN, you're usually going to have, I think, 120 ohm termination resistor. You're expecting that you've already gone through a certain impedance, and then you're trying to match it before going into the IC. So it doesn't make sense to then create another long trace that is going to create another impedance mismatch, right? So you always want this to be as close as possible to the source. So with routing, and any questions on the placement? And I'm starting to rush a little bit, but because I don't want to take too much time. Although we started a little late, but it's fine. Any questions on placement? Kind of makes sense? If not, we can do questions at the end. So the routing here, I know them as planes, but I think KiCad calls them zones. I think y'all might have seen zones. So when we're routing with planes, I always suggest, or for manufacturing purposes, to consider balancing the copper across the entire design. Whether you have 2 layers or 4 layers, for manufacturing purposes, ideally you should be flooding the entire board with ground. And this is so that you're preventing any sort of warping on the board as a whole. I noticed on some designs that sometimes there's copper concentrated on one side, and then you have a copper void. And so then if you sandwich all these layers, you're going to have a sandwich that is thicker on one side and thinner on the other. And so that makes the board prone to warping, which, especially if you're a board edge connector, that's not really good. You want that to be nice and flat. So you should have copper across the entire board. Unfortunately, this kind of adds a few other problems, but generally you always want to balance your copper to avoid this warping issue. And so by now we have hopefully already defined whether we're using a 2-layer or a 4-layer board. And we have also already thought about the stack up, like how we're using our layers. So this is just a suggestion. This is one of many ways that you could configure your boards. Generally speaking, we always want to have a nice solid reference plane adjacent to your signal plane or your signal layers. So when we're talking 2 boards, you kind of are really only routing on one board. Ideally, if you need to, you can always go to the bottom, but you want to avoid that as much as possible. So ideally, we're only routing on one layer as our mixed layer. When we have a 4-layer stack up, then we have a few more concessions, right? We can have our mixed layer with controlled impedances. We always still want to have our reference plane adjacent to our signal layers, but then we can have power planes and then more mixed signals, right? So at this point, we're supposed to determine where are we going to have our power plane, if we need power planes, or if we're only working with 2, then we're going to have to route the power, right, with traces, nice thick traces. So with power planes only really need to reach the extents of, I guess, the vias that are punching in. It's not the greatest example, but it works enough. In this case, you don't need to just use rectangles. What I could have done on this design is just add another zone over here to reach that 3.3 volts, but we're routing it with a trace for some reason. But you don't need to cover the entire board with the same plane, because the current is not going to reach the edges that is not demanding any current from it. If no current is being pulled up there, then I don't need the plane to go all the way up there, right? And so then that's why you use the copper to go around the entire thing to keep it balanced. And between the planes, for at least a class 3 PCB, you want 25 mils clearance. So from this plane to this plane should be 25, from this plane to this plane should be 25. And so this is all set up on your, I guess I talk about it later, in the zone manager. It's not in the board setup, it's in the zone manager. So when you actually create the planes or the zones, that's where you can define the clearances from the planes to the other planes or to other copper. Another important thing about routing is component pad balancing. So this is only starting to be a problem when we introduce the ground plane. Sometimes in designs, especially high-powered designs, we like to bury the pads in the plane. So in this one, since it's particularly high power and high thermal dissipation, we have flooded the entire pad with copper around it. So you can think of all of this copper as being an extension to the pad, right? And so the copper is acting as a heat sink. And so what that means is when you're trying to solder it, you know, all of that heat is being pulled away from the solder point and you're not gonna get good contact. And so this is problematic, but it's necessary in this case, especially with these sort of MOSFETs, to get that heat away, right? Especially when we're driving high switching frequencies and high power. So sometimes it's a necessary evil. But we can't do it to everything, because I see this thing right here and I forgot to include the other thing. So we have a buried pad over there, but I don't know if it's buried down there. And I'll get to that in a bit, because if we don't balance our copper, then we get tombstoning, where if we have good contact, like not too much copper on this side, like here, this is an example. We don't have too much copper here, but we have hella copper over there. You know, we're risking that at the point of soldering, our component is going to tombstone. So where we got good contact is going to lift up, right? So in this case, there's a risk that over here, since there's not as much heat being pulled away, that our component actually lifts up from this side because we don't have a lot of heat, you know, heating up the solder joint. So we get a cold solder joint and our thing is lifted, and that is no good. And so that's what happens when you bury everything. And so what you need is thermal relief on especially smaller components, where instead of flooding the whole ground pin, because all of this is ground, I just have some thermal spokes. And you can define this in your thermal, in your board setup, but also your zone manager, your thermal spokes. Because if you notice on this side, I only have a thin little trace going up. So if I flood this whole thing, then we're gonna have some tombstoning. So we add this thermal relief. So it's basically some space around the pad so that it's not drawing away that much heat. And so you get a nice, more reliable joint, and you prevent tombstoning. In this case, like, it's gonna make your life a lot easier if you don't tombstone. This is particularly important when you're like mass producing things and you have a lot of components. But in this case, you can like visually see that the component is lifted. But save yourself the rework and just thermally relieve your components, especially if they are a 0402 package or smaller. Those are the most problematic. So 0402 components, tiny little SMD components or smaller, have this issue. So never, ever flood those pins if they're that tiny. This is a bigger package, so less problematic, but still a risk. I didn't learn this one until I was in industry. So again, we've talked about long enough signal traces acting as transmission lines. And so this is what we've talked about, the controlled impedance. And generally speaking, as we've mentioned, we want to keep our traces as short as possible to minimize these effects, right? And so this is why we're always routing our critical signals first. And ideally, you should be avoiding any sort of via transitions. Now, all of the boards that I got to see, most of them needed some sort of via transition, which is fine. Sometimes it's a necessary evil. But if you do need to do this crossover, always cross at a 90. And so I chose this example because it does this pretty good. Because this is preventing any sort of crosstalk with VREG. So SLC and SDA don't have a lot of copper where they are meeting, so there's no crosstalk, plus the signal directions are different, right? In this case, we're diagonal, and diagonal, it's a 90. 90. Over here, they're crossing each other, but they're crossing each other also at a 90. So always route your critical signals first to avoid via transitions, but if you do need via transitions, cross at a 90. Simply a reminder to double check your trace widths. Ideally, we've defined these already. We have done the calculations when we did the board setup. So always make sure that your traces are actually routing that way. Like when you actually start routing it, is it doing what I expect it to do? Is it at the thickness that I expect it to be, right? Just always make sure you do that as you're routing, so that when you go back and do the review, you don't have like something that's wildly off. For power, there's a calculator for how much of a trace width you need, depending on how much current is going through that trace, as well as how thick the copper is. So that's the current carrying capacity for it. And so there's a calculator for it. Rule of thumb, I think for the most part, y'all are under an amp. 20 mils is more than enough on external layers. If you're running power on internal, I'm not worried because I expect y'all are using planes. And so riding over planes, you're usually going to be more than enough. But if you have to route internally, since you don't plate over, you're usually going to need wider traces. But use a calculator. They exist. Don't route with the minimal clearances. So here I have two examples of basically the same sort of routing, right? In this case, they are pretty close because they kind of have to be, right? There's not too much space, but you definitely do not want to be just squishing all your traces together, because these are all using the minimum clearance that we gave it. And the risk here is that these can couple with each other and they can start cross-talking, which gives signal integrity issues. And also if they're too close, like manufacturing clearance close, then that just makes them harder to manufacture, producing a lower yield where there's no reason for it, right? We have a lot of space. We have so much space over there. We use it, right? We should be using it. This is my own design that I did way back when. So this is me talking to my past self. Differential pairs, you always want to make sure they're as tuned as possible. So with differential pairs, you want to keep them as short as reasonably possible. They should be matched as close as possible. If you need length matching, you can use sawtooth. I think this sawtoothing is a little too wide. I would recommend it to be shorter and to add another tooth. You can play around with that. There's no hard set rule, so don't worry about that. And also avoid via transitions. Obviously, in this case, we're going into a connector. There's nothing really we can do about that. But avoid the via transition as possible. Try to be as symmetrical as we can with diff pairs. So usually these are going to be our can signals. So vias are cheap. Use them for the most part. We've already gone through some examples on why we wouldn't. But where you would see vias for current dissipation, we go back to this nice example where this is carrying a lot of current, driving away a lot of heat. Rule of thumb, one via can handle about an amp. Really it's closer to like 1.5 amps. So these vias are pretty darn good. If we're keeping everything under an amp, you almost never need more than a via. In this case, since we need a lot of heat dissipation, that's why there's a bunch of vias, I would assume. And so that's how you can use vias. But if you are using high power, do consider roughly one via for every amp, and that should be more than safe. Then you also have stitching vias. So this is where you would stitch multiple plane layers. So in this case, this design had a ground layer. And so these stitching vias are stitching into the reference ground, and then the other ground they have down at the bottom. And so this keeps the ground layers very well stitched. And so we also see that in this example, right? Where we have a power plane, and then this is also a power plane. And so we have both power planes nicely stitched so that there aren't too many voids, right? Because we don't want to overpower a single via with an amp, right? That's why we stitch them together. And then we also have shielding vias. So shielding vias, this is where we want the ground to be going through the entire board. We also want to make sure that whatever EMI signals are going off of this stay in there, or whatever EMI interference could be going in stays out. We do that with stitching vias nice and close. When we're talking RF frequencies, which are very short wavelengths, we want to space these at about 1/4 of the wavelength. This is extremely overkill. You're almost never going to need stitching vias for a CAN bus, but this is just kind of an example on how this works, because I think I saw on one design where I think they used 2 ground traces to kind of shield. Don't do that. Use vias. And this is especially why you want to have copper on or ground copper on all of the layers, so that these stitching vias actually do something, because they're not going to do anything if they're not connected to any ground, right? So you can also use vias for shielding. This is more or less how that will look. So if you had an RF trace going up there, this is roughly what you would see. And if it's like a really high power one, then you might have like multiple rows of shielding vias. Again, don't ever do that with diff pairs. That's never necessary. The one bad part about shielding vias is obviously on other layers now you can't really route through there, because that's almost like a wall, right? So only use it when necessary. You can get away with not using them, but they exist, and that's a use case for them. And also minimizing the return path. This might look overkill since we already have a ground connection, but since we are focused on minimizing that return path, that return loop, always put a via next to a pad, so that makes an even shorter return loop instead of having to go all the way out and then back. Right? If you track how the current loop goes. So always put ground vias next to the pads. Not in the pads, because you don't need them, but very close to them. And so some pitfalls is, as I mentioned, crossing over split planes. So here we have a meso signal. In fact, I forgot to mention here, since there's a void here, now my return current has to go way up there, and then way down here, and then way up there. And that's adding a lot of inductance. And maybe on a meso signal, we probably don't want that. So let's try to avoid creating these planes whenever possible. If this was a 4-layer board, that wouldn't be a problem, because I don't think we'd be routing on the second reference layer. But on 2-layer boards, this is a very big problem. Because we don't have that solid reference plane if we do have to do this. So that's why when you do the replacement, you want to make sure you have as straight of a shot as possible, because if we are going to have a bunch of vias, we want to be careful that our return current, or that our trace is going over copper, because otherwise we're looking at big loops, which is just only degrading our signal. Avoiding copper voids, and this is more of a manufacturing thing. This should honestly have a bunch of vias in there. Instead, there's that void. Not the biggest deal, but you want to have a nice solid ground, especially under ICs like your microcontrollers. Like this is an AdMega. That should be a solid ground fill. So be aware of those. And if you can add vias, ground vias, add them. Like I said, they're cheap. Or look for ways to kind of reroute a few things to add back some of that copper. Crosstalk. This one hurt my soul when I saw that one, because essentially what we have here is coupling, where these are on opposing. This is only a 2-layer board, so top and bottom, And so here we have signals on top of other signals. And so those are now coupled together, electromagnetically speaking. And so that's a big no-no. You never want to, be on top of another signal ever, right? So always avoid that when you can. That's why if we do have to cross over, we cross at 90s, not immediately over. This is still passable because you're still crossing. Ideally, it would be a 90, but this sort of angle is okay. But this, you never want to do that, ever. So sometimes if you have that dense of a routing, you might want to consider 4-layer boards to have at least some grounding in between those layers. And then via stubs. Via stubs is an interesting one. Ideally, I don't want to see this. I can't imagine seeing this on 2 to 4-layer boards because we don't have that many layers. But if Formula ever decides to go to a 6-layer board or above, or if you ever look at creating higher layer boards in the future, if you have a through-hole via that goes all the way through the board, but our via connection only goes from the top layer to an internal layer, what's left of the via is called a stub. And so, for example, on this stack up over here, we have a through-hole via, but for whatever reason, we're only making a connection from layer 1 to layer 2. That means we have this massive stub, roughly about 47 mils of a stub. That is an antenna, and that is going to bring in a lot of noise. And so all of this noise, since this is all connected, right, is going to degrade that signal to hell. So you always want to avoid having these massive stubs. So if you do connect signal to signal to an internal, try to connect it down here where our stub is only 7 mils instead of 47 mils. I don't think I saw any of this in any of the boards, but this is why you want to have, at least in 4-layer boards, grounds on all layers, right? Because otherwise, if you have, for example, a ground on the top layer, a ground on the second layer, but you don't have a ground down here, then all of a sudden your ground has an antenna connected to it. And that's not good, because that messes with your reference. So you want to make sure that even if you're a power plane down here, or whatever your stack up may be, wherever your references may be, that you have connections at the opposite ends of the board. This is easier on a 2-layer board since you're only connecting from top to bottom and there's no stub, but this is going to happen on 4-layer boards if you don't pay attention to them. So it's something that exists and something to be mindful of. Trace fingers doesn't exist if you don't have any ground pores on signal layers, but since I'm recommending y'all add copper pores, something that is going to happen is you get these little fingers, and so these are also antennas. And so in this case over there, that antenna is around CAN signals, and so that could affect the signal integrity of that CAN bus or those CAN signals. And so ideally you want to remove those or find ways of removing them. There are different ways of doing that. One easy way is by setting on the zone manager what do I call it? The minimum copper width. So in this case, if my minimum copper weight is or copper width is 0, just put wherever you can, then you get this little trace, this little antenna, which is what we call it a finger. But if you have a big requirement where you need at least, say, 20 mils of copper, then this is not 20 mils, you're not going to get copper over there, and that's not an issue anymore, right? And so those are different ways of looking at that. It's not the end of the world, but best practice is to remove these where possible. And so this is where I was talking about the trace to plane clearance. So as we saw in the previous example, that plane is only 10 mils to the trace. And so ideally we want to have a spacing of around 2 to 3 times the trace width. And so if my trace is, in this case it's 8 mils. If I have an 8 mils trace, I need at least 24 mil clearance to avoid any coplanar effects, right? Especially if I'm trying to control my impedance. So you want to have, you know, a bigger space from your trace to your plane. And so you can tell the difference, right? Like it's very clear that here we have a nice big trace to plane clearance, over there less so. And this is something that you set in the zone manager. So the zone manager, this is where you set the clearances. And so you can set the clearance. This clearance is going to go from copper to any copper. So that's going to go from plane to plane and also plane to trace. So that's nice and simple. Your minimum width, you can increase that as much as you need in order to get rid of fingers. 15 is okay enough, but you can increase that a little bit. You just want to avoid too many voids. This is also where you set your thermal reliefs. 20 mils is too big. That means you have a 20 mil trace and a 20 mil gap. I recommend 10 and 10. That's a pretty good thermal relief, especially since we're using small traces. Or ideally are using small traces. And then this is where you can set the order. Like if you have multiple planes on a layer, like you have your ground plane, but then like little internal planes, this is where you can set, you know, the importance of which. And you kind of have to be careful about that, because if you don't, then if we see a bunch of planes down here, those are being overpowered by the planes on top, right? And so if, for example, I needed a 12 volt plane over here, and I'm just exaggerating, but that 12 volt was down here in importance, I'm just gonna have a big copper, I'm sorry, all of this ground is gonna be covering that. So this is where you get to set that, and you can play around with that on which zone is on top and below. You can go up and down using these arrows. So that's the zone manager. You know, fairness, I didn't discover it until I was doing this presentation, so no worries if you hadn't seen that before. And then straightening traces where possible. You just want to keep everything as short and direct as possible. So little meanders like that are not necessary, or also, you know, little bends like that. This is nitpicky. This is more like when you're at the very end of the design and you're just wanting to make sure that everything is as nice and clean as possible. That is something to look for, unnecessary meanders. Ideally, they should be avoided at the beginning of the as you start routing, but it's something to keep an eye for, and it's easy to fix. And then generally speaking, we want to avoid routing underneath sensitive ICs, because if you have any high frequency signals going in, then those can permeate into the IC and ruin the integrity of the IC. Minimizing via transitions. As I mentioned, that top one, it's a through hole. We could have just gone in from the bottom layer, right? Because now adding that via transition is just adding more noise that we don't need. As parasitics, this is a 4-layer board, I think. No, it's a 2-layer. And then over here, there's no reason for us to go down, up, and then down again if we could have just stayed down the whole time. If we just stayed on the bottom layer this whole time, we save ourselves 2 vias that are just degrading our signal. So it's good to use them where necessary, but let's try to minimize them, because each one of these vias are only degrading our signal more. So it's something to look out for as you're routing, especially complicated boards. This is a big one, avoiding corner sharper than 90 degrees. There are electrical ramifications to this. So for example, if, think about your current flow. If my current is flowing from the left to the right, then I have to go up, down, and then cross that corner. That is going to create a hot spot. And we don't want that, especially if it's high current. if this is branching off, it's less bad. But what I would do here to change that is move that up where it splits off over there so that it splits off at a 90. Because right here what we have is an etch trap. And so the way that this gets manufactured is you have a solid copper sheet, and then you have an etchant, which basically removes copper. And so these corners can trap some of that etchant liquid. And so if that gets trapped in there and gets powered on, there's a chance that it ignites. And that's happened before, where a little bit of etchant makes it ignite if powered. Usually in high power situations like a high voltage card or whatnot. Generally, best to avoid these all the time, because this also reduces the yield, and it's just poor practice. Sharp design or sharp corners, 90-degree corners exist, and they have a purpose. But for most digital signals or most digital routing, it's best to keep everything in 45s, or in this case, if you're branching off like a Y, the 90 is okay, because technically you only have a 45 and a 45, right? Not a 90. Questions with routing? The Fab Prep is going to be a lot quicker, I promise. Yes?
So you said when branching, 90 is okay, but when generally everything else, try to keep the corners at like 45 degrees, right?
Yeah, generally speaking, because you want your, and this also comes down to, funnily enough, impedance matching. If you've seen any RF circuitry, you'll notice that they all have curved radiuses, right? They curve nice and they flow instead of having 90s, and that's also for impedance matching. In this case, it's not as important, but basically, when you're turning a corner, right, you're traveling more on the outside than the inside, right? And so I guess if you were to think about why we're having this hotspot is because, you know, the current is going to flow that way. And then with 90s, you kind of have the same issue, right? If you're just kind of going a 90 corner, right? That's why our cars have differentials, right? Right? And so if your current has to go at a 90 degree, that's going to create a hotspot in the inside of the corner all the time. In this case, you can get away with a 90 because you're branching out that way. But if you're coming in and going up 90, not as good. So always think about where your current is flowing when you do these designs. And so when you're reviewing the designs as leads, think about where the current is flowing across the board. Where is the power flowing across the board, right? So that way you can just look at the board, look at the traces, and immediately detect, is this flowing nice and straight? You know, do I have any weird jagged corners? Can we improve this any way, shape, and form? If you're revising a previous design, think about, you know, are these 90s creating any hotspots? Because sometimes, especially with high current, you're going to be able to feel the hotspots, right? Either from 90s or because your traces are too thin, because sometimes that also happens. Like that's why you want to have as much copper as possible when you have power so that it gets dissipated, right? Generally speaking, avoid 90s when possible. When possible. And so there's different ways of writing this. Like I said, just bring that up, make a 90 for a Y split. But if you're coming in from different angles and you need to go 90, avoid it. Yeah. Any questions, other questions? Well, I can go into Fab Prep and then open up for questions, generally speaking. Solder mask clearances. So you will hopefully have noticed that you have a solder mask layer. It's F mask or B mask, so front mask, back mask. And so this is where you can choose to tent your vias. It literally has tent vias front and back, right? So if you want test points on the front, but you want everything on the back sealed off, for example, if I'm going to be on top of a chassis and I don't want any metal contact on the bottom for whatever reason, then you can tent those. But if you want, test points at the top. You can choose not to. And so what that's going to do is create solder mask clearances. And so wherever you see purple or pink in the design where there's solder mask, that's a negative. So that means that there isn't solder mask there. So that means if you see purple around a via or around a pad, that means that's exposed copper. And so everything else is not exposed copper. Everything else is covered by the solder mask, which is the green or whatever other color you choose to have on the board. Historically, you always go with green because green on white, since it's nice in the middle of the color spectrum, it's nice and easy to differentiate pads, components, solder mask. So that's why we've always seen green on white. Typically, test equipment is blue, and then I forget what red is for. I've usually seen that on like motor drivers and stuff. But anyway, so solder mask layer is a negative. And so when you're doing your silkscreen, you want to make sure that you're avoiding solder mask openings, because this right here, this is the back solder mask. So this is where you solder a pin. This is exposed copper, or should be exposed copper. And so this solder mask is not gonna, this silk screen is not gonna adhere to this, right? And so if you want a nice continuous silk screen, which I guess doesn't matter too much here, but ideally if the manufacturer is getting this as a stencil, they're gonna put this on the board and silk screen, and so there's gonna be residue on this. You don't want residue on that, you want nice clean copper. So you never want silk screen to go on top of your solder mask clearances. And so that's something to check. You can do something with the DRCs to check that. So the design rule checker, which I'll go over in a bit, but otherwise it's kind of easy, just visual inspection, like, oh, if you turn on the silk screen layer and the solder mask layer, you will see it. So I checked most of the footprints, and generally speaking, the footprints have solder mask outside of the silk screen outside of the solder mask, so that shouldn't be an issue. The issue is going to be when you add other graphics. So it's just something to be careful of, especially if you expose your vias, right, if you're not tenting them. So the design rule checker, that's this button up here. Ideally, you shouldn't have any errors and you shouldn't have any warnings. Some of these errors and warnings you can ignore because it's something about the datasheet field, not as important. But the DRC is going to tell you if you're violating something like a trace got too close to a via pad, or your traces is too close to something else. Like here it's showing where the DRC violations are, but I don't trust them too much. So you should always, ideally, you should be doing this as you go through the design, but especially in the end, just to make sure that you don't have any manufacturing errors or errors in manufacturing, because ideally that doesn't matter. The unresolved text variable is not a problem, but for example, if you do have, say, a trace that is crossing a different component pad that is not like the same net, that's a problem, right? Because all of a sudden you're shorting two nets. You don't want to short nets. This is a good start. Now, in industry, what we have is, or what we've realized in industry is our EDA can only do so much. The DRC can only detect so much. What we do is actually check the Gerbers. In industry, we have something called the ODB++, which is an intelligent database that has the design. In this case, we're just using Gerbers. And so what I always recommend is checking the actual Gerber files. Now, KiCad has a Gerber viewer. However, I would recommend looking at something else, because your manufacturer is not going to have KiCad Gerber viewer. And sometimes the KiCad Gerber viewer might omit a few things. And so this is an old Gerber, so it's not accurate. But what I'm seeing here is I turned on the top layer. I turned on the, what did I turn on? I think the silk screen and the board edge, right? So you want to make sure that your board edge is correct. You want to make sure that your copper is correct, because I see some copper extruding over here, which looks a little funky. This is on a copper layer, so the manufacturer is going to see that as copper and it's going to be like, what is that? So always look at your Gerber files to make sure that there isn't something funky. And you can turn on different layers. Like this is where you can check your silkscreen on solder mask. You do not want those to be on top of each other. Silkscreen on solder mask. Or you also want to make sure that these pads all have solder mask. They should be. You know, if the footprint was loaded incorrectly, it should have it. But if it doesn't, then you might have to create it. This is also where you can check sometimes the clearance from the trace to like a void or a copper pad. I'm not going to go through a whole design. If you want, I can probably pull one up. But so always check the Gerber files, especially as leads, right? You know, y'all are the last check, and so this is the stuff that manufacturers are going to build off of. And so it's your responsibility to make sure that the design is actually what you're intending it to be. And so it's always good to have the design open, have this open, kind of compare, you know, like, all right, why does this look funky? Go over here. It's like, huh, I didn't see that before, and try to correct it, or guide the other engineer to also correct it. Oh, there's a CAN bus. But so Gerber files, always take a look at them. And then, as I mentioned, surface finishes, they have their pros and cons. We're going from cheap to expensive here. HASL is a good glove fits all solution. This is the cheap and easy way to go, but if you want something more reliable, consider immersion gold or ENIG, or the hard gold for the edge connectors. That's kind of all that I have. Oh, I'm not going to go too much into the documentation. I don't know how y'all do your documentation, but always try to keep a good record of everything, of every design decision that you make, right? So the moment you get the schematic, or even while making the schematic, like, what are the nets that have certain requirements? Like, what are the nets that need the controlled impedance? Because not everything is going to need to be 50 ohm single-ended, right? Only some things need to be. Or what is the impedance of your differential pairs, right? Or what is the current of your power? What is the current that is going into different power components? And so having that on record gives you something to look at and has something concrete to reference when you choose the trace widths. You know, how much copper do I need for 3.3 volts? Am I going to surpass an amp? Probably not, so I'm probably fine. But always keep a record of that, whichever software, whichever way you do. Keep a record on why you chose 4 layers, what those 4 layers are, or what the 2 layers are. That way it's easier to go back later on in the design. It's also going to make it easier when debugging. So whenever you actually get to build the design, right, you might not be the one that's overseeing that testing. Hopefully you are. If you design it, it'd be nice for you to also test it. But if someone else is testing it and is noticing some discrepancy, like, this should actually be like 120 ohm differential. Like, where was this the decision taking? Why am I seeing so many reflections coming out of this component, out of this IC? Is this a problem with the IC, or is this a problem with the PCB design, right? And so always try to keep a good record of every decision that is made, right? And that's kind of all I have for the PCB basics. I know I focused a lot on the manufacturing side of things. But all sorts of PCB guidance should follow if y'all have a way to access it. The standard is the IPC 2221. It's currently in revision C. If you have a way of accessing the standard, if maybe the library can order it, that's going to tell you everything about like the current industry standard for PCB design. Otherwise, you can reach me via email or also through LinkedIn. If you're curious about some other niche bits about PCB design, or if you want me to take a look at a design that you're doing for formula, just reach out and I'll do my best to be a support. But I open it now for any questions around the miscellaneous concerns. I know I just bombshelled a lot of information. It's hard to choose everything about or share a lot about PCB design because there's just so many quirks and things about it. But yeah, that's a little nutshell intro to PCB design. Any questions? All right.
I have a quick question.
Yeah.
This far way back, so I don't know if you can pull up the slide, but when we were looking at the, I forget if it was like, you called it like micro.
Yeah, the VIAs, the VIA types.
Not the VIAs, split lane and, or I don't remember the names, but you showed a picture where there's like copper, green, copper, green, copper.
Okay, so in this, the stack up.
Yeah.
This one or
Maybe a couple.
this one?
Can you go down like 20? Yes. So like looking on like the bottom left image,
Yes.
like was that like a subset of like a 4-layer board? Is that like what you'd be seeing? Okay.
Yeah, so this is basically like, if this was a 4-layer board, you can imagine, for a reference, you want it to be a solid ground plane.
Mm-hmm.
So this is probably not going to be your top layer because that's where your component paths are. So you can imagine this being layer 2, layer 3, and then layer 4. This is kind of assuming that you are able to route all of your power on layer 1, or if you are able to route this such that your power planes are not on top of this, right? So this is going to give you the best impedance control because you're not affected by plating, and it assumes that you have solid ground references, right? But that does limit how you use your 4th layer or even your 2nd layer. Ideally, you don't want to touch your 2nd layer if you have components, solid ground. And then if you really, really want like the absolute best quality and smallest trace for controlled impedances, you could do this, right? This is something that you would see a lot more in like 6-layer boards where you have like your components, I mean, 6-layer is a little strange. Probably closer to an 8-layer board. So you're probably not going to encounter this, at least in formula, where you have like component ground, ground, signal, ground, ground, signal. So, but this is where it's embedded. So yes, you could see this in a 4-layer board where you have components, ground, your 3rd layer is a signal, and then your 4th layer is a ground. So it is possible. It just has slightly different mats. That's why I said you're mostly going to end up using that top one because it's just going to be easier to just generally do your board. And you're not working with signals fast enough where it matters too much because, let's see, this is especially good if you need like a really high, we're talking megahertz to gigahertz levels of speed and frequency. You need that. Because otherwise you would need this, and we're not touching this. Because this is basically that, but adding copper on the sides, right? And for that you need a bunch of shielding vias, and you also need to remove the solder mask, and there's more processing to it. So you're probably not going to use that as much, but it is possible. And if you're wanting to take the challenge on getting the cleanest signal, you're more than welcome to try it. This is also good on there's a special subset of boards, they're called stripline boards, where there are 3-layer boards where their only function is to carry a single trace. You're probably not dealing too much with this. This is good for when you need a very specific RF signal to travel from one board to another, and you need that shielding on top and the bottom because it's in a noisy environment and you don't have a coax cable. That's basically the time you would use something like this. It's cool to know, and I'm happy to talk about some designs that use that. I don't think you'd use it in formula because you're not really dealing with many megahertz or anything that is sensitive to it, but maybe it'd be a cool challenge to do, you know, really optimize for that signal integrity. So it is a way of doing that. So you can imagine layer 1, layer 2, layer 3, and layer 4. Or in the same way here, layer 1, layer 2, layer 3, and layer 4. I'd recommend a little bit more for that since differential pairs are a little bit more sensitive. So if you do end up doing that, you would probably end up doing it because you have a lot of these. All right, so yeah. And there's thankfully calculators for it. Sometimes with 4-layer boards though, and here's the caveat. If you remember 4-layer boards, they're not symmetrical. Strip lines are symmetrical. So that assumes that these distances are the same. There's a calculator for it as well. It'd be for an asymmetrical one where you can choose the heights, these different heights. So you probably use that. It's similar, but it's asymmetrical. So if you do end up doing an asymmetrical strip line, so if you want to really maximize that signal integrity for those diff pairs, make sure it's the asymmetrical one because it's not symmetrical, because that's pretty far. But that does exist. Generally speaking, I just don't think we're using anything high frequency enough where it's necessary. It'd be a cool challenge, but not necessary. So, something to consider. Maybe on an 8-layer board, like a motherboard.
I remember you talking about a sawtooth cutter, using that to like length match the potential signal.
Yeah.
Is that something that you'd have to do like manually, like go in and check the length of one trace and like try to match it with the other, or is that like a function of the EDA?
Normally you should be able to. Normally there should be a function where you can tune the differential pairs. Where is it? Yeah, tune the length of a single track, or in this case, since it's a differential pair, it'd be the skew. So it's that button right here, tune skew of a differential pair. That's what you would use. And I'm not sure what KiCad does, but I think you manually tune it, right? So you manually choose how much tuning you need. And you can typically check down here the routed length. So this track is now 19,000. Am I reading that right? Yeah, 19,000. I guess 19 inches and 778 mils. And this one's 400 and... Well, it wasn't even tuned right. Normally you want to tune them to be within 100 mils difference. In this case, I'm looking at 300 mils, and that's exactly how they had it tuned. So really, it should be the other one that's being tuned, but I can see why they tried that. This is, I think, the motherboard. HV motherboard. I would double check that tuning because that didn't look right to me. But yeah, so that you would do that with a route and tune the skew. Sometimes you can also do other serpentine tuning if you need different nets to be the same timing. So for example, if you need your MISO and MOSI, for whatever reason, they need to be tuned to the same. They're not a differential pair, but you would have to tune a single track, right? Or if you had two differential pairs, you all don't have any of these, but if you had two differential pairs that between the differential pairs, they have to be like the same distance, then that's when you would tune the length of the whole differential pair. But just for one or one half, you would tune the skew. And the way you would check this is, I mean, it gives it to you right here, right? The routed length. You just check the routed length. And if the routed length is over 100 mils, that's when you would tune it. Yeah, I don't know what they were doing here. And normally, I don't know if there's a way to change it here, but there we go. You don't want to tune too high. Really, this should be tuned at most one spacing out. So if our spacing is pretty close, we want the skew to also be that, because otherwise you lose coupling, right? You want to keep this coupled the whole time. And so you have to, thankfully this is manual, you have to adjust it here, right? So where it was, that's way too big. You're decoupling. Really, this should be closer to here. And when you lose that height, then you kind of compensate by adding more, right? So that's how you would do that. And that's, like I said, you want to do that so that they're close to or within 100 mils. In this case, we're tuning the wrong one. So if we ever rev this up, I would check that CAN bus. But yeah, that's how you do that. And I think CAN is the only thing that you route differentially, I think, in your design. So you don't have to worry about it too much. But yeah, that's the thing. If you have any other burning questions, I'm happy to answer them here. I use other EDAs. So I use what used to be Mentor Graphics is now Siemens. I use Expedition. It's kind of the industry standard now. So it was an adventure going back to KiCad because I still only had like KiCad 6 on this. So I wouldn't be an expert in KiCad tips and tricks, but I could probably point you in the right direction if you need them. Yeah.
So you mentioned with if you're doing a VIA for like an important signal, you could shield that with like ground vias.
Mm-hmm.
Could you maybe like talk a little bit more about that?
I mean, do you want to know the whys or the hows?
How would that look like a circle like kind of around it, or like?
You just need one. So for example, this is a VIA transition and I do not like this CAN routing. This is hurting my soul because this is not differential. This is a differential, that's not differential. But if we were to, I guess let me turn on the other layers and make sure I'm not, okay. So in this case, let me just move this to at least look a little more differential. Ideally, these should be coming in straight, but okay. So it's pretty simple. Let me place some vias. Ground vias, please. Route, place vias. You can literally just do that. That's it. That's all you need. You wouldn't use 5-volt vias. Let's see. I forget how to do this, but you would want it to be ground vias regardless, and you should have a ground layer, so I don't know why.
Press E.
E?
And then change the direction.
Yep. I need to refresh myself with all the key bindings, but but yeah, so shielding is not too crazy with this. Like that is more than enough shielding. So if you do have differential pair transitions, just having a ground vias on each side is going to help your signal a lot. Because sometimes people forget to do that, and it degrades the signal quite a bit. So doing that helps a lot.
So it's important for transitions?
Yes, always. Ideally, like especially when you're doing Impedance control, you always want to have shielding vias because those are your most critical signals. In theory, you could do it for all transitions, but that's overkill half of the time because a lot of signals are slow. But in this case, you're, 500 or 50 kilohertz? That's considerable. So ground vias are only going to be better. They're only going to benefit. When I had shown the differential pair with all the shielding vias, you could, but that's just overkill. It's overkill in that case. But over here, you do need them. Yeah. Yes.
That board that you're showing us, that one goes in the accumulator, so that board has had historically a lot of EMI issues. Are they caused by any of the way that we have any of those traces routed right now, or?
I would say yes. I like the shielding that it has, but I would say it could be better because depending on how many, on the frequency of the board or the frequency of everything, those vias should be a lot tighter, right? Maybe not a quarter of an inch tight, or I'm sorry, a quarter of a wavelength, but it should definitely be at least a wavelength, stitching all the way across. I do notice, so is what you're measuring, like measuring outside, or is it just that the signal integrity inside is not great?
We don't have exact measurements. I know the previous elite before me, actually, this is the second revision of this board. There was a revision Mark 6, and back in Mark 6, there used to be a lot of EMI issues where if you stuck out an oscilloscope probe with, you stuck it out like a circle like this, you could see like a 60-volt spike in EMI.
Yeah, so the problem is this board is running very long traces, and if it doesn't have any impedance control, because I see differential pairs and everything, but if these were not checked for all the things that we said, you just basically have huge inductors. Because we just saw this CAN bus that is 20 inches long. That has a lot of parasitic inductance, because that is a huge trace. And so all of these huge traces, they're all doing that. And so you just basically have a huge loop or a huge inductor with this huge board. And so I would say that's probably it. What helps here is checking this controlled impedance, because I'm pretty sure, this isn't helping. I see it's a solid reference plane, but this could use a lot more grounding vias or shielding vias. I see some sense lines on the bottom layer that are not properly referenced. So I see this right here, right? These sense lines that are crossing these split power planes, and those are causing huge loop inductances because they don't have a reference. Or if anything, here, they would have to go here, but what's hurting this is these are sense lines. They need a ground reference, but their current reference is power. You're referencing 12 volts and 5 volts, or 5 volts and 12 volts. And so your loop is having to cross 2 layers to find the ground. And furthermore, you're crossing these power. So I would be very careful with these detect lines, especially over here where these are spaced so closely. These do not need to be that close. So yeah, there are some things that are definitely not helping this. Like, this has no reason to be routed like that. And again, since all of this is referencing power, if there were short traces, not a problem. But this, let me see. This is 7 inches. If you look at your transmission model line, that is huge. Then we also have these signals that are coming all the way from the edge of the board. So on a board like this, I would really even go higher than a 4-layer board so that you have good shielding within all of those sense lines, because you just have huge inductors. Those are like, that being 7 inches is crazy. And so if you're not referencing it correctly, you don't have any shielding because you don't have any ground below it. Your next ground is layer 2 and you're on layer 4. and if you remember the stack up, even though it's a 4-layer board, if you're down here, routing down here, and your next ground is over here, and if you're doing that for 7 inches, or if you're doing that on the can and that's, what, 20 inches? That's a massive loop across the 62 mils of the board thickness. So if this ever goes to another rev, I would consider increasing the layers since there's a lot going on. Also, what's not helping, generally speaking, I don't think this voiding is helping you. I know why you're doing it, but then you also have these unshielded lines. And if anything, these are probably causing you the most headache. And I'll tell you why. You can get away with not having any traces on the first layer. And in this case, you have some traces. You can get away with those traces. But you gotta realize, I mean, sure, there's quite a bit of voltage, a significant amount of voltage, right? It's a high voltage card. You can get away with ground pretty sure on the second layer. Now, yes, you do need, since it is such high voltage, you do want to avoid having a ground too close. And, you know, you probably want to model this before doing any huge design improvements. But regardless of how it is implemented, these floating traces are not helping, are generally not helping. Do we know how much current is going through these? And also that
Most will be 2 amps.
how much?
At most, theoretically, it would be 2 amps.
These are too thin. And then these, I assume sense lines? Oh, these are LEDs. Yeah, I just don't like that there's absolutely no ground. There's no return current. Like, where are you closing the loop? I guess you technically are routing it, but it's just such a huge loop because basically, instead of keeping the loop localized underneath the trace, you have to go all the way around. Don't take my word for it, because I don't work high voltage or high power. I would model this somehow. I don't think this is the full story. I just don't like that. Because even for the LEDs, I mean, they do draw power, and they are in the loop. So I'd look at that. It's probably not the whole story. But I wouldn't be afraid of adding more layers to this. Because you can get away with, I think, 6 layers for 1.6 millimeters, still reasonable. If you go 8 or 10 layers, you can look at 80 mil thickness. I think an 8-layer board might be okay for this, simply because you have so much going on. Something to consider. Because it's so big, it would get very expensive. So maybe it might be worth getting another revision on this where we do a little bit more shielding before we crank up all the layers. I'm not sure. It'd be good to get a bunch of eyes on it before taking any drastic decisions, but I will say having such long runs of ungrounded or unshielded traces and sense lines, not great. but not the end of the world. Because I do see that here you also connect to a bunch of other cards. And so if those are also not correctly grounded, like have you all looked at the grounding scheme? Like, I'm not an expert in this, in necessarily these systems, but I see they all go to the same ground, but is there a chassis ground that this is all supposed to be connected to?
They're all connected to the low voltage battery, which is also connected to like the physical chassis of the car, outside the accumulator. But that corner over there, that's connected to a different ground. The part that doesn't have
the copper. Yeah. I'm just thinking you might need that other reference. Either that second reference or another thing that I'm looking at this, I'm just not sure it's grounded right because you have 3 different grounds or 3 different boards connecting to one big board. You're assuming that they all have the same ground, but that's not necessarily true because they have their internal local references, but then you're expecting that to reference. It might be fine. You just have to double check your grounding scheme. It's worth taking a look, at the very least, at a system level, because this is a system, right? Because you got these 3 boards that are all operating on a ground, and we are assuming that those all have that same ground that we're connected to, which I guess we're connecting to here. Because I see these grounds. Is this battery ground or is this chassis ground?
Those are actually isolated. The only ground is that box by the IMD latch. Through that amp seal, we connect to the rest of the ground of the car. So a little bit below the little frog icon.
Yeah. I'll just double check it. I don't think it hurts to look at the grounding scheme of the whole system, just to get a sanity check, because that is a big voltage spike. Yeah. Yeah, I'm not sure. At least design-wise, I can tell you the things that I see wrong. System level, you know, needs a little bit more time and a little bit more analysis than what I'm giving you. So take everything I've just said about this board with a grain of salt until it all gets looked at. Yeah, I don't want to send you all on a rabbit hole that isn't correct. On this design, I mean, I still question this, but, you know, if this is certain, well, I mean, I guess the first thing that comes to mind, so that is not connected to anything, right? We're certain about that? That this ground hole is not connected to anything? It is not supposed to be connected to anything? Yeah, I see an X, so I would hope it isn't. Yeah. Ideally, doing the ground, getting a ground layer would be ideal. Again, I'm not a power person. I do radio frequency design, so I can only provide so much guidance. This one was an interesting one. This is where I'm not gonna judge these, because although this shielding scheme is something I would fix if it does get revised, this relay out, although I didn't see this in any other designs. And this could also just be fixed by adding the ground all across the whole board. Because I see there's this ground here, and I think that connects down there. That's fine. But yeah, just a solid ground pour, especially under this. And then stitch it with a bunch of vias. That should be fine. If you still need to shield this for whatever reason, then you can add the vias like in the perimeter, instead of doing that. This is unnecessary. I've just never seen this before. Also, this is a hanger. That ground is, this is just a finger. It's going nowhere. So here you just have a massive antenna, because that should be grounded. So, little details. It's a dense board. It's okay for what it is. I would just be careful when routing, especially these areas. I'd even consider a 4-layer board, potentially. And in this case, I don't know how important the brakes are, because I think this is, I mean, that's what it's called, brakes. What's the name of this board?
Yeah, BSPD.
The BSPD.
This is actually the board I made my first year.
Okay. That won't be too harsh.
You should.
All right. Time to break it down. So this is a board that I would not have mind seeing as a 4-layer. I see you were able to route a lot of your power, but routing the power is also kind of what led to a lot of the via transitions. So as a 4-layer board, this could look in 2 ways. You can keep what you have and then just put 2 ground layers in the middle so that you're shielding or referencing the top layer, and then all your bottom is also shielded with solid ground as a 4-layer board. Or, because you only have one type of power, right? Or how many powers do you have on this?
Just one.
Yeah, you're 5 volt. I mean, you could also do the top layer, ground layer, power, and then your lower speed digital stuff referencing the power. How big is this card? Like 7 inches? I'd be wary of those trace links. Again, a lot of this is floating, so this is also a bit of a hazard if I'm being harsh with it. Because you have, if we look at the ground, at your ground, let me see if I can turn off the solder paste and the solder mask. Yeah, because the problem is your ground is being broken up by all of these traces. So I guess if I'm going top down, I only have ground here, this little pocket here, which leads nowhere. This actually terminates there or there. So really I only have 2 ways for the current to flow. If I turn on this, so if I'm looking at this shutdown sense, its return current essentially has to go out, find its way back in, then go back out, following the ground voids, then back out, follow this ground void, go into this ground, etc. Have you had many issues with this board?
Yes. Oh, so many.
Yeah, I would add more ground layers. That's where I would start. Also, these via transitions need, well, you have good grounding, except, or you've grounded these, but ground traces are, I would avoid them. I would start with ground pour on this layer, because right now it's just traces, out ground pour. It should help. And you ideally want to have each ground, I guess I didn't cover this, but you'd like to have each component to have its own ground. That's why we added the vias into each ground pad. Because if you're sharing the grounds, like for example, you could consider this meso via transition, although I would just kind of avoid, no, I don't know. I would do this a little bit different. You could consider these grounds to be like a sort of shielding, but that's also the ground that is coming out of this connector, which is fine, but also the ground of this LED, which is not recommended. It should have its own ground via. I wonder why some of these grounds are going so far out. Not the end of the world, but it's miso. Maybe this reset could have gone out, and then the miso could have just gone. It's worth another revision. I would at least add some layers for better grounding. That's where I would start. Also, this antenna is not great. It's, wow. Yeah. Because this is at least terminated here, but this isn't. Yeah, start with that. This one, geez. This one's actually fine, because this is what this board did right. Sure, it's very tight and it's a lot of crosstalk, so I would try to increase the footprint of this so that you get more room. But the redeeming grace is that we have solid ground all throughout. So even though it's huge, these traces are huge, but it at least has a short enough return current because your copper is immediately below. This is another one where, I mean, it would also help to have the copper in the top layer so that you also have some shielding immediately next to the traces, if possible. This one's okay. Okay enough. We look at BPSD. This is the BMS core. I think I already went about that. Anything about the suspension strain? Oh yeah, this is the one with the miso. Yeah, because for example, in this case, if we're already going down on this layer, what we could do is just accept that we've already gone to the other layer, and instead of going all the way down to go back up, is move this via up so that these can at least cross nice and straight. Ah, geez. I need to work on the key bindings on this thing, but right. And so this is nice and straighter, and all of a sudden well, there would be a void there. But what we can do is just avoid that void. And if we assume that this this trace were straight, you know, that's a lot better, I would say. And then you could fix all of these other ones. I would look to see if we can reduce the amount of vias going on. As I mentioned, just making this a straight shot. Although, since it's a via transition, it's not too crazy. But I would be a little careful about these 90s if they were higher speed, because it's essentially a 90 through the board and then another 90 through. Not the worst, but you ideally want to be at a little bit of an angle. These 90s, I'd be wary of these 90s. I would just go a straight shot and then a straight shot. Because then if you look at the current flow, right, this 5 volt goes in this trace and takes a 90 here, we have a hot spot there. That's fine. It was one of these boards that I saw Well, I don't see the bypass capacitors on this, and I'm pretty sure there's a microcontroller. Yeah, so for example, I would expect pin 4 and pin 5 to be VCC. So I would prioritize that bypass. I'm assuming one of these is the bypass capacitor somewhere. Whichever is 5 volts and ground, I would assume that's probably the bypass capacitor. So this is why it's important to look at the schematic, right? So generally on a bunch of these designs, it's good to revisit that, because otherwise these 5 volts, where is it? This 5 volt is only getting it from this via, and this via is not really doing much justice. That's not good. So, you know, there's always room for improvement on all of these. Yeah. Any other questions that isn't necessarily going through these boards? Yeah, thanks, Outlook. If not, I'll let y'all go. We're an hour over. But thanks for listening in, and hopefully next year as y'all start or take on as leads, you'll have a bit of an eye, and when y'all actually do reviews with folks, maybe as the design process goes, try to help out your fellow engineers, right? Because a lot of this I got from, but I'm sharing what I kind of wish I knew when I first did this when I was in Formula, because I got no direction whatsoever. And I would hope that in the future of Formula that, you know, we at least give a little bit more guidance and instructions. And with PCB design, there's just so many caveats to everything, you know. It's good that y'all now know a little bit more about this, where some of the issues can come from. And I hope that y'all will continue to instruct your PC board designers with some of these tips, tricks, and whatnot. So, yeah, thanks for being here.